Imagine our third known visitor from another star, 31ATLAS, lining up not for a harmless flyby, but for a direct hit on Earth, a 1-kilometer chunk of rock and ice, slamming into our planet at over 60 kilometers per second. In this video, we're going to follow that impact moment by moment, from the first flash in the sky to the last. Consequences for life on Earth. 3I/Atlas is what astronomers call an interstellar object, a traveler from another star system that just happens to be passing through our solar system once before it disappears back into deep space. In reality, it is not on a collision course with us. But to really understand how dangerous something like this could be, we're going to imagine a what-if scenario. What if 3I/Atlas did not miss, and instead crashed straight into our world? For this thought experiment, let's set some basic facts so the rest of the story makes sense. We'll assume 3I/ATLAS is about 1 kilometer across, roughly the size of a big mountain, made mostly of rock with some ice mixed in. And because it's falling in from interstellar space, we'll give it an impact speed of about 60 kilometers per second. That means it could cross the distance from London to New York in under a minute. That speed is much higher than most normal asteroids that hit Earth. Now, where does it hit? To keep things simple, but still realistic, imagine it comes down near a major coastline, close enough to land to dig a crater, but close enough to deep water to throw up enormous tsunamis. That combination land impact plus nearby ocean makes the situation as bad as possible for both local and global damage. With those assumptions in place, let's move into the final moments before impact and see what people on the ground would actually experience long before 3I/ATLAS reaches the surface. People in the impact hemisphere would notice something strange in the sky. Even in daylight, a blinding point of light would appear, growing rapidly brighter as it tears into the upper atmosphere. At 60 kilometers per second, the air in front of the object is compressed so violently that it heats up too. Temperatures hotter than the surface of the sun. The rock itself is wrapped in a sheath of plasma, leaving behind a brilliant, burning trail across the sky in the last few tens of seconds. The object is screaming downward at many times the speed of sound. Smaller meteors might shatter or explode high in the air, like the Chelyabinsk event in 2013, but a solid 1-kilometer body at this speed doesn't simply break apart and vanish. It punches through the atmosphere almost intact, carrying nearly all of its kinetic energy down to the surface. Then, in a fraction of a second, everything changes. When 3I/Atlas finally strikes, the energy released is beyond anything our civilization has ever witnessed. A rough estimate for a 1-kilometer stony object hitting it around 60 kilometers per second gives an energy on the order of 10 to the 21st joules. You don't need to remember the number. What matters is what it means. Tens of thousands of times more powerful than the largest nuclear bomb ever tested. Enough to erase an entire region in a single, brutal instant. At ground zero, the rock, the ground beneath it, and a massive volume of atmosphere are all vaporized instantly. A fireball tens of kilometers wide blossoms out in milliseconds. A crater perhaps 20 to 40 kilometers across is gouged into the crust, hurling rock and dust high into the sky. Everything within tens of kilometers of the impact point is simply gonna vaporized, pulverized, or blasted into the air at lethal speeds. As we pull back from ground zero, the devastation continues to spread. Within a radius of a few hundred kilometers, the blast wave from the impact tears outward faster than any hurricane wind. Buildings are shredded, forests flattened, and anything standing is knocked down. At the same time, a pulse of intense thermal radiation from the fireball ignites fires far beyond the crater rim. People hundreds of kilometers away could suffer severe burns just from the flash in the sky if the impact is near the coast. As we assumed, the effect on the ocean is just as terrifying. Billions of tons of seawater are instantly displaced. Walls of water rise and race outward as tsunamis, heading across entire ocean basins. Coastal cities that never saw the crater itself could be hammered hours later by towering waves that flood far inland. All of this destruction, the crater, the fireball, the shockwave, the first tsunamis unfolds in the first minutes after impact. But the disaster doesn't stop there. The next 24 hours turn a regional catastrophe to something that begins to involve the entire planet. As the shockwave from the impact ripples through Earth's crust, seismographs worldwide would register a massive earthquake centered on the strike zone, easily reaching magnitude 9 or more near the impact. aftershocks would rattle the area for days. For those on the other side of the world, the first sign of what happened might be a sudden burst of seismic activity, followed by broken communication links and confused, fragmentary news. Meanwhile, the tsunamis unleashed by the impact fan out across the oceans. Depending on where 3I Atlas hits, coastlines on several continents might be struck. Hours after the initial impact, waves tens of meters high crash into distant shores, smashing ports, flooding low-lying cities, and dragging debris and people back out to sea. Even well-built coastal infrastructure is not designed for this kind of event on land. Far beyond the immediate blast zone, shockwaves continue to travel through the atmosphere. Windows shatter hundreds of kilometers away. Weak structures collapse. Fires started by the thermal flash spread through forests and cities, especially if emergency services are overwhelmed or destroyed. Energy grids, roads, and communication lines across an area, size of a small continent, could be badly damaged or wiped out for people living anywhere within that huge impact hemisphere. This day becomes the worst day in recorded history. Millions dead in hours, major cities destroyed, and entire regions cut off from the rest of the world. But even that is still only the beginning of the real threat. What truly turns an impact into a global crisis is not just what happens on the surface, but what gets thrown up into the sky and how long it stays there. When a 1-kilometer object hits at this kind of speed, it doesn't just dig a hole. It excavates and vaporizes enormous amounts of rock, soil, and water, launching them high into the atmosphere, sometimes even above it. Some of this material falls back down as scorching ejecta, starting secondary fires over a wide area, but a significant fraction ends up in the stratosphere, spread out as fine dust and aerosols that can circle the planet as days turn into weeks. This veil of particles begins to block a noticeable portion of the sunlight reaching Earth's surface. The sky may take on a hazier, dimmer look. Sunlight becomes weaker. Average temperatures, especially on land and away from the oceans, begin to drop. Growing seasons in key agricultural regions might shorten. Crops that were already vulnerable to drought or heat stress now face cold snaps and reduced light. This is not necessarily on the same level as the great dinosaur-killing impact 66 million years ago, which involved an object perhaps 10 kilometers across, an order of magnitude bigger than our 3I Atlas scenario. But even a 1-kilometer impact can create something like a mini-impact winter for a few years. Colder weather, disturbed rainfall patterns, and repeatedly failed harvests in parts of the world that feed billions of people in a modern, highly connected civilization. You don't need every city to be physically destroyed to trigger a global disaster. You just need certain key systems to break. Major ports, grain exporting regions, critical manufacturing hubs, fuel supply lines. Combine that with a few bad growing seasons, and suddenly you have food shortages, economic collapse in vulnerable countries, and intense political pressure everywhere. So, in the months after a 3IA cell impact, the world might face not only the direct physical damage, but also a web of secondary crises. Refugees leaving devastated coastal zones, shortages of essentials, financial systems under stress, and rising tensions between nations. The initial flash of light in the sky has now become a prolonged test of human resilience and cooperation. What about the longer term? If we move the clock forward several years, the picture slowly changes again. Over time, most of the dust and aerosols injected into the upper atmosphere would settle out or be washed out by rain. The sunlight would gradually return to normal levels. Temperatures would climb back toward their previous averages. On geological timescales, Earth has shrugged off far worse events than this and continued without pause. But for human civilization, the recovery would not be so simple. Regions closest to the impact might remain uninhabitable or economically dead zones for decades. Entire national economies tied to now flooded ports or ruined farmlands could fail to recover. Many species, already stressed by habitat loss and climate change, might not survive this extra blow. Would humanity as a whole be wiped out by a 1-kilometer interstellar impact? Probably not. There would almost certainly be large populations of survivors far from the impact zone, especially in regions that are geographically protected, else less dependent on global supply chains or better prepared. But the global population could shrink dramatically, and the technological and social complexity of our civilization could take a massive hit. In some areas, people might be pushed back toward a far simpler way of life, not by choice, but by necessity. In other words, an event like this is not the end of the human story, but it could easily be the end of the world as we currently know it. All of this raises an obvious question. Why focus so much on an object like 3I Atlas? The reason is that interstellar objects are, in some ways, the most challenging kind of impact threat we can face. They move faster than most asteroids native to our solar system. Their incoming paths can be highly inclined or unusual, making them harder to spot with surveys that are tuned to find more typical near-Earth objects. And because they come from far away and only pass through once, our warning time could be shorter. Today, there are global efforts to find and catalog near-Earth asteroids and comets. Dedicated telescopes scan the skies every clear night. Space agencies are planning and testing ways to deflect or disrupt dangerous objects long before they reach us. The more we know about an object's size, shape, composition, and orbit, the better our chances of doing something about it. The good news is that impacts by objects as large as are imagined, 3-1 Atlas scenario, are extremely rare on human timescales. And again, in reality, 3-1 ATLAs itself is not on a collision course with Earth. This entire scenario is a way to understand the stakes. Not a prediction of what will happen, but thinking through this, what if, teaches us a lot. It shows how much damage a single kilometer-scale rock moving at interstellar speeds could do. It reminds us that warning time and preparation are everything. And it puts every new interstellar visitor into perspective, not just as a scientific curiosity, but as a reminder that space is not empty and that our planet lives in a dynamic, sometimes violent cosmic environment. So, if 3I Atlas really did crash into Earth, we'd see an unimaginable explosion. The destruction of an entire region, tsunamis racing across oceans, and a global crisis that could reshape human civilization for generations. It wouldn't necessarily erase our species, but it would test us in ways we have never experienced before. If this journey helped you visualize what an interstellar impact would truly mean, and if you learned something new about how fragile and yet resilient our world can be, consider subscribing to the channel. I'm building a full series on 3I, Atlas, and other extreme space what-if scenarios. Using real science to explore the wildest possibilities. Let me know in the comments what you'd like to see next, the safest places on Earth to survive an impact like this, or the technologies we might use to actually push a dangerous object off course. Because in the next episode, we're going to explore a different kind of close call. We've just seen what happens if 3I Atlas hits us. But what if it just missed and passed as close as the moon instead? Turning our night sky into the brightest and most terrifying light show in human history without completely ending civilization, that is the scenario we'll dive into next.